Chapter 14, Part 4. So this part, you may want to go through this a couple times. This can be a little bit complicated. You maybe want to stop right here before you go even any further and read through the notes first before you even listen to the lecture, then listen to the lecture, and then go back through the notes. So we're going to talk about reaction mechanisms. So when we talk about chemical equations, typically the chemical equation shows the reactants and the products in the reaction. And there's really no information about the steps on the molecular level as the reaction proceeds to products. So the steps in the chemical reaction that we never really actually see is called the reaction mechanism. And so it describes the order in which the bonds are broken and formed and the changing position of the atoms. So there are some reactions that, as you see them, are called elementary reactions. They don't have steps to them. And those can be defined by what we call their molecularity. So the number of molecules that participate in these elementary reactions. So there are some that occur in single steps. Most do not. Most have multiple steps to them. So as A goes to products, if that's an elementary reaction, we call it unimolecular. If there are two reactants that go to products, we call it a bimolecular. So we have uni, we have bi. And then if there are three reactants that go to products, we call it a termolecular reaction. So a balanced chemical reaction occurs in a sequence of elementary reactions. So here's my first example. So if I have two NO2 molecules colliding and they transfer an oxygen and they form this. When you see a reaction mechanism, you're going to see a step identified as a slow step and a step identified as a fast step. That's really important. Okay, so the summation of these two equations lead me to my one final equation. And how do they sum up? Well, I can see that I have NO3 on the product side here and an NO3 on the reactant side here. They cancel out. I see that I have one NO2 on the product side here, and I have two on the reactant side here. So one of those reactants will cancel out. So now I bring down everything that I have left, which is going to be one NO2. It's going to be the CO. It's going to be the one NO from the slow step. And then finally, the CO2 from the fast step. Okay, so that's my final reaction. And so this NO3 that is first formed, all right, and then it is used up as a reactant, that is called, the NO3 is called an intermediate. And that's important because it doesn't show, you can see that it doesn't show in my final reaction. And so when I look at a reaction pathway for one of these reaction mechanisms, it's going to look a little different than the one that we saw in the last part of the lecture. So I would start out here at a low energy with my reactants. Then I would have what I call this transition state where there is an energy of activation, an activated complex formed. Then there's going to be that intermediate. When the intermediate forms, so in my example above, that intermediate that would form would be right there, okay? And then once that intermediate forms, the rest of the reaction occurs. Again, I get another energy of activation, another activated complex, and then it progresses on to products. So what we can see like we could look at this and we could say, which one of these would illustrate the faster or the slower step? Well, look, it's going to take a greater amount of energy to get to this first transition state versus getting to the second transition state. So from this, I can see that this part, my first one here, is going to be my slower step versus my second step here, which would be my faster step. So this would be the first transition state, and then this would be the second transition state. So the height of the peak for each step in the mechanism will tell you something about the rate of that reaction. Then over here, I just did another quick little example where you get this intermediate forming. So let's say A plus B leads to X plus D. Then I take that X and I react it with some more B and I get C. So what happens here is that that intermediate crosses out, is not part of my final equation. So I have A plus 2B goes to C plus D. And so my rate expression for each step is, when I have these individual steps, my rate expression just uses the coefficients. I don't have to go through all that work that I did earlier in the lecture part 1 to determine order. I take those values for the order with respect to those reactants directly from the coefficients. This, you can only do it this way when you have a mechanism where there's more than one step to the reaction. So again, here, this one, there's an assumed 1 there, and so then there's an assumed 1 here for the order of that reaction. And then I'll talk in a minute about how you identify what the overall rate expression is for your final equation that you develop. We'll talk about that in a minute. Okay, so this is just another example where you have a unimolecular and a bimolecular, and they sum up to this one final equation, and I took out the intermediate again. So the rate law is ultimately derived from the steps in the series of the reaction that lead to the one final reaction. And so if the reaction is only one step, then you can do what I said before on the previous slide, where if it's one step and it's just an elementary reaction, you can use your coefficients to identify the order, okay? If it's bimolecular and it's elementary, so again, be careful, this is only true if they are elementary. And so if they're identified as elementary reactions, you can use those coefficients to identify the order, okay? But like I said, there are not many reactions that have this, what we call elementary characteristic. Most of them are from a series, and that's why we go through what we did in the first part of the lecture to identify those orders M and N. Okay, now, so for these multi-step reactions, these mechanisms, the rate law can be determined. You can determine the rate law from one of your elementary reactions, and it's always going to be your slowest step. This is very straightforward, so don't read into it too much. So if I know that these are my two equations for my mechanism, right, to get my overall equation, and these have been identified from my data, usually in a question like this, these speeds, slow and fast, are given. So all I have to do is go to the slowest reaction, and I can treat that slowest reaction as though it were an elementary to help me identify what the rate expression would look like. So that's my slowest. That's the most important one. It's as simple as you can only go as fast as your slowest step in the process. So if I pick my slowest step, then my rate is going to be dependent upon the rate constant and the coefficients that are there. Okay. And so if I just combine my two NO2s, it's going to be K NO2 raised to the second power. And so this would, if you went back and you did a whole rate data study on this, you would find that this rate expression agrees with experimental data. So then here's another example here that you can try. If you want to give it a try, maybe if you don't get it, you could ask me questions on it during office hours. I think it's a great one to try and see if you can do that. And of course, there's some in the problem set that you'll be able to work through and see the answers for. So then there's one last thing that can be a little tricky. So it's mechanism when the fast step is the initial step. That gets hard. So you'll see that when you have these double arrows in your first step of your reaction, and it's identified as fast. When that's the case, what you have to do is you have to redefine the concentration of this one product. Okay, because what it's saying is that that product doesn't hang around very long. The reaction reverses, it flips around and goes in the other direction. So when that happens, you have to rename these species. So what I've done here is I've walked through the steps on how I rename that NOBr2 to equal K times the concentration of NO times Br2. And then I can go and plug that value for my slow step, right? Because in my slow step, I have that NOBr2. And since I'm saying it doesn't hang around very long, I redefined it. I redefined it as this from here, and then I plug in the other reactant in that slow step, which is the NO. And so now I have an expression for the rate expression. There's really two Ks, but two constants really end up being just one constant. And so I have NO raised to the second power times Br2. Okay, so that's going to take a little bit of work on your part. Again, here's another example that I would say give it a try, see if you can make it work. And if you can't, see me for some help on it. All right, good luck.